Okay, let's talk about complex one, right? We're right here at the beginning of the electron transport chain. As I mentioned last time, this is the receiving point for all those NADH equivalents. All the NADH that's made in the TCA cycle and or glycolysis that can be imported and run through this process is going to enter the electron transport chain right here at complex one. Okay, so how this work how this works has been a fascinating focus of people trying to understand the sort of not only the redox chemistry but the functional chemistry, the structure function aspects of this complex for a long time. And what was known for a long time is that this process first involves transfer of the electrons to a tightly bound flavin mononucleotide, right? So remember FAD, right? Where we have this isoalloxazine ring connected through this ribose, then to adenine dinucleotide. We had a phosphoester and we had adenine on the other side of it, right? Well, flavin mononucleotide is the same sort of electron receiving or transferring business in, but without the adenine, and it's tightly bound. It's not exchangeable. It's tightly bound in sort of the receiving active site of this complex where NADH is brought in, right? And FAD or FMN, these flavonoids, if you recall, can take up electrons and protons in a sort of one electron, one proton, two steps of one electron, two proton transfer, right? So if you have the FMN, the fully oxidized form, this molecule will first take up on that central nitrogen that's not in that nitrogen, sort of not in that bond that's connecting the sugar, the nucleotide. The other nitrogen will take up one proton and one electron to generate the so-called radical or semiquinone form of that isoalloxazine ring. The second addition will then happen to that nitrogen, that aromatic nitrogen over in this sort of diketone ring, to now fully reduce the molecule now to the hydroquinone or FMNH2, right? Directly analogous in terms of electron transfer to what we talked about with FAD back when we first started thinking about metabolism, right? Now, that transfer clears the NADH, gives us NAD plus back, but that's sort of just the beginning of the process, because within the structure of this molecule, it had been known for a long time that there were iron sulfur clusters. Remember, we talked about iron sulfur clusters with respect to aconitase when we were thinking about metabolism earlier. But now, whereas aconitase was using this to run a hydration-dehydration reaction, the iron sulfur clusters in this case are absolutely focused on moving electrons around, right? So the electrons have been known for a long time. They're going to come out of the FMN and they're going to go through some iron sulfur clusters. And they've been known for a long time that complex one had a couple of different types of iron sulfur clusters. You can build these in multiple different ways. They're so-called two iron, two sulfur clusters, where you have a couple of iron centers. Two coordination positions are taken up by cysteines, and then you have a couple of inorganic sulfurs. And then you can also build this in a cubic arrangement with 4 irons, 4 inorganic sulfurs, and then 4 cysteines, right? And these different iron sulfur clusters work out or turn out to be really great ways to push electrons around, right? The electrons will happily flow into these irons and then move from position to position. Now, exactly how this worked, right? How this movement worked, and how it was connected to proton transfer, which we'll talk about in a little bit, was a total mystery for a long time. People had really no clue, and there are all kinds of crazy ideas about how this might work. And then with advances in cryo-electron microscopy a couple of decades ago, people started to get the first sort of view of this, right? The mammalian form of complex one is huge. This thing's nearly a megadalton in size. Really hard to work with, right? It's a membrane protein and it's gigantic, right? So until cryo-EM came along, it was really kind of a mystery how this would work. But the first early low-res cryo-EM structures indicated this thing was kind of an L-shaped molecule. It had this big sort of lobe that stuck out into the matrix, and then this long piece that then extended out into the mitochondrial inner membrane, right? So again, here's the matrix, here's the inner membrane space. Protons are going to be going this way. Electrons are being transferred to the FMN, and then this somehow moves through this electron transport chain. And then ultimately, these are going to get pumped into our receiving molecule, this coenzyme Q, that is going to do a sort of an organic molecule of electron transfer, analogous to what we just saw with FMN, right? So coenzyme Q is this aromatic diketone, right? Fairly simple molecule that's connected to these long chain isoprenoid units, right? So if you think about that in the context of the lectures that Dr. Carr just gave you, you can imagine where that stuff is going to be, right? You extend these sort of these isoprenoid units out to like, 14, 16 carbons. This thing is not going to be soluble at all in solution. There's no way. Those isoprenoid chains are going to happily solubilize themselves down into a membrane, and that's where coenzyme Q lives. You can sort of think about it as being dissolved into or soluble or diffusive within the inner mitochondrial membrane itself, right? And that's where coenzyme Q lives. All right, so in the matrix, we transfer these electrons out of NADH. They go through FMN, this iron sulfur cluster, transfer somehow, and then they get ultimately transferred into coenzyme Q in a sort of a similar two-step process of one electron, one hydrogen, just like we saw with FMN, where we first reduce one of these ketones in coenzyme Q to an alcohol, right, to create the ubiquinone or semiquinone or radical form, because we've only put in one electron, which results in one of those electrons ending up sort of on this other oxygen. And then the second electron proton transfer now gives us the dialcohol or dihydro or hydroquinone form, also known as ubiquinol versus ubiquinone, right? Okay, now the question is, how is this all happening? And again, this was pretty mysterious for a long time, but half a dozen years ago or so, maybe a little less, someone solved a detailed structure. I can't remember if it was a crystal or maybe a crystal, combination of crystal structure and high-res cryo-EM of a bacterial, a simpler form, smaller than the mammalian form, but basically built under the same set of principles. And we learned some amazing stuff about this, right? And so this is what the structure looks like. So here's that L-shaped molecule, right? Here's that piece that's embedded down in the mitochondrial membrane. And here's that piece that's sticking out in the matrix, that big lobe sticking out in the matrix. Now, it turns out the NADH oxidizing active side of this molecule is right up here, because right there, you see that little green guy? That's the flavin mononucleotide. So the NADH reduction is going to be happening right up here. We're going to take NADH and make NAD+, right? Okay, so those electrons are going to end up going into that flavin mononucleotide. Now, notice something, the coenzyme Q, it's down here in the membrane. How do those electrons get from here down here? Well, if you look, you see these little guys here, these little clusters? Those are a whole set of iron sulfur clusters. And look, they run kind of like a wire, like they're heading right down towards the membrane, right? You can imagine now the idea that the electrons maybe would flow down through that little electron wire towards where the coenzyme Q is. Okay, that's cool. But if you look closely, you'll notice something else. Are those iron sulfur clusters touching each other? Does it look like a wire? The way you think of a wire, like you plug in, I keep using that analogy, plug into the wall and get electricity into your laptop. No, they're gaps. They're holes. Think about it in between, right? These guys don't, and this is a real structure. These guys do not touch each other. So how do the electrons get through there? Number one. Two, how does this thing pump protons? Right? I mean, you can sort of begin to rationalize electrons. They've got some metals here, something's going on. But how does flowing of electrons over here through this sort of matrix localized lobe, how does it result in protons going from down here out here? Excuse me, going from out here, right? Because remember, this is the matrix inside, and this is the intermembrane space. Not obvious, right? At all, right? Okay, so to address that question, we've really got to think about a couple of things. how does electron transfer work? Number one, in sort of a general sense, and in systems like this. And then how could proton transfer actually work? How could directional movement of protons actually work? Okay, so think about that. Let's think about electron transfer first. So we have these two iron sulfur clusters, right? We've got, say, we got an iron sulfur cluster here, and maybe we've got one over here. The electron's over here, maybe on the left side of my little drawing here, and we got a gap, right? Now a classical particle, right? If we have a full-on gap, right? A classical particle can't exist in the gap. You're done, right? You can't move the particle across the gap if it can't exist in the gap, right? But if you remember our discussion about quantum mechanics way back when, and this idea of wave functions, and we specifically talked about it really with respect to absorption of light, and absorption of light by the electronic system of or chromophores, we understood this idea of sort of energy levels, and a description of this process of moving these electrons around required this sort of idea of a wave function, right? All right, so to extend that idea a little bit, you guys may or may not remember that everything in principle has a wave function, right? An associated sort of effective or de Broglie wavelength. Electrons, because they're so tiny, they're so itty bitty, their wave properties are just as important as their particle properties, right? Even though you could calculate a wave function for me, right, or a table, its effective de Broglie wavelength is so stupid small, it's for all practical purposes, it's not even worth thinking about. But for electrons, that's not true. All right, so an electron that approaches a gap like that, even though the particle itself, the physical particle, if you want to think about it as a classical particle, can't cross the gap, its wave function can, right? So you think about this electron sort of bouncing up against this gap, you know, and here's the sort of high probability, sort of an idealized sense of the wave function over on the left side of the gap. Even though at the gap, that wave function drops exponentially off pretty substantially, on the other side of the gap, the wave function is not zero, which means, if you think about this another way, the probability for the particle to exist on the other side of the gap isn't zero. All right, so here's another way to think about it. Here's, say, our electron oscillating back and forth, right, sort of running up against that gap in an iron sulfur cluster. Here's the gap separating the two iron sulfur clusters. The probability, the highest probability is the electron, it's just going to stay there, right? It can't do anything, it's just going to bounce off. It's oscillating around in the orbitals of that iron sulfur cluster. But the probability of it not being there, all right, because its wave function spans that gap, and because we know the uncertainty principle dictates that over small enough distances, we can't specify position and velocity simultaneously accurately. What that means is that the electron has a finite, a non-zero possibility of simply appearing on the other side of the gap, right? That its wave function dictates that there is a non-zero probability that the electron can simply not be on the left side and can now be on the other side of the gap, right? This is, of course, something known as electron tunneling, right? You've probably heard about it. Tunneling is a very strong function of the distance between, say, two centers that electrons could migrate across, right? It's this sort of like exponential decay here is sort of captured in the fact that if we think about the probability of the rate of transfer between two centers, right, that could, in principle, hold the electron, right, and one at a higher redox potential than the other, so there's a driving force between the two, it drops off, the rate drops off, these are log, right? It drops off as a very, I mean, many orders of magnitude as you increase the distance. When they're directly in contact, you know, transfer is extremely fast. But by the time you get out to a distance of about 10 angstroms, if the gap is filled with nothing but vacuum, the transfer is essentially zero. Now, a couple of things that affect this. One, that will move that curve around. One is the potential, right? How strong the redox potential is between the two centers. A really strong potential, you can transfer across a wider gap, all right? The other thing that matters a lot is the medium in which it's embedded. If those two centers, instead of being in vacuum, are surrounded by sort of the electron clouds and whatnot of, let's say, amino acid side chains, right? You embed our centers into a protein, you can push that curve over quite a bit, right? You can get that maximum distance of transfer, right, over to 20, 22, 23 angstroms, something like that, or a little bit further, depending upon, again, the redox separation, right? Okay, so this is key because this idea of tunneling, of the sort of jumps from the FNN to these iron sulfur clusters, is exactly how these electrons are going to migrate down this path, right? And we load then the coenzyme Q binding site is right here, right, at that interface between the membrane and where the sort of elbow or neck, I guess, between the matrix domain here and the membrane domain. And the electrons can now jump right into that coenzyme Q. That's cool, right? Now the question is, how does this pump protons, right? None of that explains how this thing pumps protons, right? If you remember in sort of in the previous slide, if you go back and look at that, the production of the hydroquinone form of coenzyme Q, that's net going to take up one proton out of the matrix, right? Because the production taking NADH to NAD plus, right? That's going to leave one proton here, but that formation of that hydroquinone form, that's going to take up a proton, right? In order to get the go from the oxidized form of coenzyme Q to this fully reduced form of coenzyme Q, right? That's going to take up one proton from the matrix. But this thing pumps a whole lot more. It pumps 4 protons, essentially, for each one of these that pumps 4 protons. This is sometimes known as a chemical proton that's been removed by the coenzyme Q reaction here. But there's actually 4 protons per reduction event that are also pumped. How does that happen? Well, that was a total mystery for a long time until this structure was solved. And what solved it, right, is going to turn out to be something about how that thing is put together. But the speculation for how this worked went around a lot of different ways, right? And there were 2 sort of ways in which, in a general sense, people thought this might be happening. So one is this idea of a so-called redox loop, where, say, you had something happening asymmetrically on one side versus the other of the membrane. For example, you had something being oxidized, right? Something that here, these 2 protons and their electrons that are then transferred into something in the membrane or part of a protein complex, right? And then you have an oxidizing event here that's on the same side, but these guys sort of move in some sort of a diffusional cycle constrained within the membrane, so that as they move up here, the electrons transfer over to this oxidizing guy. They reduce the electrons in, say, this A group, sort of an idealized thing, reduce the B group, right? Whoops. Oh, no. Come on. Okay, reduce this B species, and in the process, because you do this only on sort of this one side of the membrane up here, you've now, by moving where these guys are in the membrane, you now allow for an asymmetric movement of protons across one side, because you do this sort of electron transfer between A and B here on one side versus the other side, right? So when you reverse it on the other side, you can now take up electrons, right? That's the idea of a redox loop. And people thought complex 1 might work that way for a long time. That's kind of how it was taught to me, but it absolutely made no sense how it worked. I mean, it was just like, maybe this is what happens, right? The other way in which people thought this might happen would be some sort of a conformational change. So you could imagine having a protein conformation that would take protons on one side of the membrane, and by virtue of those protons being taken up, the protein would change its structure. Maybe would like flip around in the membrane and now release them on the other side of the membrane, right? This is sometimes known as a conformational pump. In principle, there are examples of both of these, it turns out, in biology, but it wasn't clear at all how either one of these would work for complex 1, right? All right. So again, the solution to this came down to the structure, right? So we've talked about this matrix-facing lobe where the flavin mononucleotide and the iron sulfur clusters take up the electrons. I pointed out that the coenzyme Q binding site is going to be right down here, and those electrons are going to come down here into coenzyme Q, right, to create the hydroquinone form of the coenzyme Q. The cool thing was when people solved this bacterial structure, it just the answer to the problem just immediately dropped out, right? Because it turns out that what these the membrane embedded chunk of this thing sort of has 4 domains. They're all stuck together, right? But each one of them, here's one, right? 1, 2, 3, 4. Each one of these guys is a direct structural analog of another type of transporter that was really well understood, a so-called sodium potassium antiporter, right? That are used to basically, as a result of a salt gradient, move proton or use a proton gradient to pump sodium ions across a membrane, right? But they're the direct structural analog. So here's the way people now think this works, that when the electrons move from that last iron sulfur cluster and reduce coenzyme Q, that basically communicates an allosteric signal to this little array of pumps in the membrane. And when you make coenzyme Q, that conformational, that sort of binding change, when that happens and you populate reduced coenzyme Q in the active site, sort of some kind of an active site down here at this sort of neck, each one of these pumps basically opens and pumps a proton. So you get 4 simultaneous protons pumped out of the matrix through these little sodium potassium light antiporters into the intermembrane space. The coenzyme Q then diffuses away and the pumps close. And you do that each time you run one of these electron transports. The pumps open, pump 4 protons, and then close as the reduced coenzyme Q diffuses away. Okay, so that's how we begin the process for one branch of reduced electrons into coenzyme Q. Now we need to look at the other branch that puts electrons into the coenzyme Q pool in complex 2. And we'll start looking at that in the next video.